today's video lesson, we're going to start talking about chemical bonds. So finally, we actually get into some real chemistry, at least the perception of real chemistry, where we're going to look at putting elements together to make new chemicals. How do sodium and chlorine actually make salt? How do hydrogen and oxygen actually make water? What electrons are being used? How are they being used? And how do they stay together? So what we're going to do is this first section is just going to kind of give a general overview, and then we go into details with three very specific types. So after this general overview in section 2, we're going to talk about covalent bonds. In section 3, we're going to talk about ionic bonds. And in section 4, we're going to talk about metallic bonds. Which ones are we going to use the most in this class the rest of the year? It's probably a toss-up between ionic and covalent, probably a little bit more ionic. So that's why I have it listed as number 1. It's maybe a little bit higher priority for our course that we're going to be using them for, but the book introduces covalent first. So we're going to talk about each one of those. Now, the two that we'll talk about the most are going to be covalent and ionic, not so much metallic bonding. And when we get to that section, we'll talk about why. But just quick overview here. Covalent bonds. Basically what's happening here is atoms are going to share electrons to bond together. Okay, remember, the electrons are basically the glue that will allow atoms to bond together. So we're going to talk about covalent bonds where they're sharing. Now we'll also talk about, is it equal sharing or unequal sharing? And we will get into more detail with that in section 2. The terms just to remember with the different types of sharing: polar. Okay, think of polar opposite, two ends, two unique ends like a magnet. Okay, or North Pole, South Pole. That's unequal sharing. And then nonpolar covalent is equal sharing. Again, for this section and this section only, since we're kind of introducing it, we just need to be able to understand what the word means, and we'll get into more detail later. Then, when we get to section 3, we'll get into much more detail about ionic bonds. Exactly how many electrons are going to be gained or lost, which ones are they going to be, how much, where do they go, where do they come from, and all the different things related to that. The difference with ionic bonds, there is no sharing. It's a gain and lose, and opposites attract. So they kind of go together like two magnets. Whereas in covalent, they're kind of two atoms that are nearby, that stay nearby so that they can share electrons. Again, we'll get into more detail later. So how in the heck do we figure out, just by looking at the elements, what are they going to form? Real simple calculation here. We're just going to look at electronegativities. If we look at the electronegativity of two elements, and then we can figure out the type of bond that they will form. Now, we're keeping this simple. We're not going to look at 3 elements or 4 or 5. We're just going to look at 2 at a time. Keep it simple. Now, general rule. Of course, there can be little inconsistencies, and then what if there's a 3rd atom or a 4th atom? That sort of throws it out, out of whack. So, very simple calculation. Now, when we do this calculation, never is really any one bond 100% ionic or 100% covalent. It's kind of somewhere in between. And this is a relative scale. This is not something we can measure. This is a scale or a number or a value that gives us a description of the type of bond. Our 3 choices are going to be ionic, polar covalent, or nonpolar covalent. Again, we're not including metals in this. So really all we do is we look at the 2 elements that were in question, we look up their electronegativities, and from their electronegativities we're going to figure out the type of bond it will form. Now, remember about electronegativities, the simple definition. Certain elements are going to have a greater attraction for electrons, other elements are going to have a lower attraction for electrons. So if we think of the definitions here of the different types of bonds, if we come back here to the previous screen, if we have something covalent, we probably have electronegativities that are maybe somewhat equal. Now, if it's polar covalent, they may not be as close because if there's unequal sharing. If they're nonpolar covalent, that means that the values are probably almost identical. If they're ionic, then that means the electronegativities aren't even close to each other, because we've got something that's dominant that's going to take and something that's dominant that's going to lose. So we'll get kind of the extreme, the opposites. So look up the numbers. Here's what we do. You need electronegativity chart. When we do this, on the homework, obviously you'll need to get this out. For taking a test, I'll give you a copy of the table. All we do is we look up the numbers. The calculation, one of the simplest calculations we're going to do all year. To determine the bond type. Now this scale is on page 176. You will also be given this. This is not a 100% absolutely positively this is the type of bond. This just gives us a picture of what it could be. The calculation, just subtract the two electronegativities. Okay? Look up the electronegativity for each element and subtract. The thing that we do here, we always subtract the higher minus the lower. So we always get a positive number. Once we have our answer, then we just look. Well, here's our range. If it's ionic, it's somewhere between 3.3 and 1.7. If it's polar covalent, it's somewhere between 1.7 and 0.3. And if it's nonpolar, it's between 0.3 and 0. Why is the difference only go up to 3.3? Because fluorine is the highest at 4.0. The lowest element is 0.7. That's the biggest extreme you can get. What if it is exactly 1.7 or 0.3? Well, then we say it borders the two. And we can say it's in between. That's perfectly fine. Because remember, it's a description of. If you look on page 177, they have a couple sample problems. They look at hydrogen, sulfur, cesium and sulfur, and chlorine and sulfur. And you can look in the middle of that page on 177. They look up the two electronegativities. They subtract to get the difference. And then they look on the chart to identify what type of bond it is. So hydrogen and sulfur, the values are 2.5 and 2.1, difference of 0.4. Difference of 0.4 falls in the polar covalent range. There you see with cesium, the difference is 1.8, falls in the ionic range. And then chlorine and sulfur, difference of 0.5, also falls in the polar covalent range. Right? That's all we do. You're going to get electronegativities. You're going to get this scale, and you just have to subtract and then find where that value fits. So we have you take a minute here or two. I'll pause this, have you pause it, and go through and see if you can figure these out. And then at some point in class, just come up, show me these, and make sure that you know what you're doing. One more calculation that we'll look at is we can assign a percentage to each type of bond also. Now this calculation is not in your book, so you're going to need to write this down. Right? They talk about it on the scale on page 176, but they never go through it. We can also, so the percentage, how do we define it? Well, the definition of the formula here I have is the percent ionic character. So if we have two elements and we figure out the type of bond, but then we want to say, well, is it a 90% ionic bond? Is it a 10% ionic bond? So this gives us a little bit more accurate picture on the type. Real simple calculation. We take the difference between the two divided by the higher electronegativity times 100. And that's it. If it's a big difference and A is a really, really small number, we're going to see a huge percent ionic character, really, really high. If we see a small difference and a big or a small value for A, then we're going to see a much smaller percentage. So if you look back on page 176, okay, or this chart, here's what we'd expect to see. If we have a big difference, if we have a big difference, then we're going to have a pretty high percentage. If we have a value of 1.7, then it's pretty close to 50. Now, the percentages on this right-hand side are not accurate. You can't say 1.7 is always 50 because remember, this is just the difference. What you need to do is take the difference divided by whatever the higher value is to get an accurate percentage. Be careful, some of the questions in the homework or in the book or on the test or whatever, make sure it's not asking for percent covalent Okay? Because remember, that's really the opposite calculation. So if you want to find the percent covalent, it's 100 minus the percent ionic. 70% ionic, 30% covalent. 70% ionic, that means most of the electrons are not being shared equally at all. Okay? Maybe a small percentage of the time they are, or a small fraction they'll be shared, but not shared equally at all. The last thing just to remember here, what do the percents mean? This is probably, out of this section, the hardest thing people have trouble with is just remembering what the numbers tell you. So just make sure you keep this straight. High ionic percentage means low covalent percentage. Electrons are being shared less. If it's a low ionic, that means it's a high covalent. Therefore, the electrons are being shared more, okay, more equally. Again, make sure that you have that percent calculation down because it is not something that is in the book. So that's section 1. And what we'll be talking next about will be each individual type of bond covalent, getting into details about that, and then ionic bonds and getting into the details of that.